welcome back. So we were in the process of proving Taylor's theorem. The second derivative test using Taylor's theorem. So so let's continue. We stated a linear algebra lemma, which, as I said, has two purposes. One is to actually prove, help in proving the second derivative test. The other is also it helps in using the second derivative test. Okay. So the linear algebra lemma is it basically says two things. Firstly, if a matrix is positive definite, if and only if all the eigenvalues are positive, a real symmetric matrix is positive definite if and only if the eigenvalues are positive. The second thing it says is, if you have a continuous matrix valued function, and if the matrix at one point is positive definite, then in a neighborhood it continues to be positive definite. Okay, so let's prove this theorem. Okay, so the first part of it. So if A is real and symmetric, okay, then by the spectral theorem, which we recalled in our rather detailed overview of linear algebra, O transpose AO is diagonal, where O is orthogonal. Okay, this is diagonal. Okay, and all these are real eigenvalues. Okay. Now, so suppose you want to study positive definiteness. So suppose you take, so if A is positive definite, okay, if this is the case, then if you take, for example, if you take, so what would that mean? If you take O transpose AO times V transpose V, this is OV transpose AOV, which is positive if OV is not 0, which means V is not 0. I'm sorry for using, maybe I'll call it theta transpose. O is probably confusing. Okay. So, but what is this, right? This is simply the diagonal matrix V transpose dV, which is lambda 1 V1 square plus lambda 2 V2 square plus so on lambda n Vn square. In other words, this is positive if V is not 0, which happens if and only if all these lambda i's are positive. Okay. So in other words, if the matrix is positive definite, all the eigenvalues must be positive. Likewise, if the matrix is positive semi-definite, that means if V transpose AV is greater than or equal to 0 for all V, then all the eigenvalues are greater than or equal to 0. By the way, why is that so? Because if you put all the Vi's to be 0 except for one of them, say V1, then you get lambda 1 V1 square is positive, which means lambda 1 must be positive. That's why these two are equivalent to each other. Okay. But anyway, so this implies also that a positive semi-definite matrix has eigenvalues which are all greater than or equal to 0. So we need to go the other way around. That is, if the eigenvalues are all strictly positive, then why is the matrix positive definite? Now, of course, you can go from here to here, it's fine, right? This is certainly true. V transpose theta transpose A theta V is positive for all V not equal to 0. For all theta V not equal to 0, but that is equivalent to all V not equal to 0 because theta is invertible. But this being positive is equivalent to this. Why? Because suppose we want to prove, what is this? This is simply, if you instead take some other vector. So suppose you want to prove that this is positive, right? So declare W to be theta inverse times V, which is basically theta transpose times V, right? Then W transpose theta transpose A theta W equals what? It is simply V transpose AV, which means this is positive if and only if this is positive, right? So in other words, this is positive implies V transpose AV is positive. Yeah? So in other words, we have successfully proven that if all the eigenvalues are positive, then V transpose AV is positive for all non-zero V. And if they are in fact greater than or equal to 0, this is greater than or equal to 0 for all V. Okay? So that proves the first part of this theorem. Okay? What is the second part? The second part is H is Rn 2Rn square is a continuous matrix valued function such that H of x is a symmetric n by n matrix. Okay. What you are told is this is the case, it is positive definite for all V not equal to 0. Okay. Right, and we want to prove for some epsilon positive. There are a number of ways to do this. So one way, for example, would be that this is equivalent to saying that V transpose H of A V is greater than or equal to C as long as the norm of V is 1, where C is positive. So by continuity, V transpose H of theta V is also greater than or equal to, say, C by 2 for all V whose norm is 1. But all these proofs, I mean, it's not obvious, it requires some work how you use continuity here. But the easiest proof for us is by contradiction, and it's also practice to do this by contradiction. So what we want is this. How do we produce a contradiction? When does this not happen? Right? What is this saying? Something happens, there exists an epsilon so that something happens. What's the contradiction to that? What's the negation of it? For every epsilon, there is a counterexample, right? So no epsilon exists, which means suppose, for the sake of argument, that no epsilon works. That is, if we choose epsilon n equals 1 by n, there exists a theta n in this ball of radius 1 by n where this fails. Is less than or equal to 0 and norm of V is equal to 1. Of course, you might object saying norm of V need not be 1, but that's not a problem. Just divide by the norm of V and you can make sure norm of V is 1. Okay? So why is this a problem? The reason this is a problem is because for some V. Okay? Right. So the unit sphere is compact. Norm of V equals 1 is a compact set, as we saw earlier, which means every sequence has a convergent subsequence. Let's call it Vn sub k, right? So Vn sub k converges to V such that norm V equals 1. Now by continuity, so theta n, of course, theta n converges to A. Why does theta n converge to A? almost by definition, right? If n is large enough, the distance between theta n and a is at most 1 by n, which can be made less than epsilon, right? So theta n converges to a. So which means h of theta n converges to h of a by continuity. V, in fact, so that means h of theta n sub k converges to h of a. If a sequence converges, every subsequence converges to the same limit. So this based here converges to V transpose H of A V. Why? Because matrix multiplication is continuous, right? This is a continuous function of A and V. I mean, as theta n converges to A, H of theta n converges to H of A, and matrix multiplication is continuous, so these things converge to V, so the product of these matrices converges to this. Okay. How does that help? It helps because V transpose H of A times V is less than or equal to 0. Why is it less than or equal to 0? Because for every element of the sequence, this is less than or equal to 0. And V is not 0, obviously, because norm of V is 1. But this is a contradiction because we've assumed V transpose H of A V is larger than 0 for all V not equal to 0. So these two contradict each other. Okay? So that's the problem. So in other words, this theorem is true. We have produced a counterexample assuming its negation holds. Right? Okay, so our lemma, linear algebraic lemma holds. So returning back to the proof of the second derivative test, since f is C2, h of x, which is d square f dxi dxj at x, hij is continuous, which means f of a plus h is strictly larger than f of a for all mod h less than epsilon, and h is not 0 if h of a is positive definite, which means that a is a local minimum. The same reasoning holds if A is a local maximum. How does it hold? Well, if A is a local maximum for f, if A is a local max for f, then A is a local min for minus f. And the Hessian of minus f is minus of the Hessian of f. And if a matrix is positive definite, minus of the matrix is negative definite. So the same result proves even the local maximum case. Now what we are left with is the case of the saddle point. So what is the saddle point? What are we trying to prove for the saddle point? So since we don't have it written down here, let me write this again for you. H transpose theta h divided by 2. Right. Now, if h is invertible, but it's neither positive definite nor negative definite, what does that mean? That means there is some vector h non-zero such that h transpose h of a is strictly negative. Likewise, there is a vector h tilde non-zero so that this is strictly positive, right? Right. So how does this help or hurt anything? The point is you have h of theta here, it's not h of a. Had this theta been equal to a, you could have concluded that if you took this particular vector h, then f of a plus h is less than f of a, and if you took this particular vector h tilde, then f of a plus h tilde was larger than f of a, right? So it would have neither been a local maximum nor a local minimum. But the trouble is, this is h of theta, it is not h of a, right? So how can we then conclude anything from this information, right? So the point here is, first of all, if h of a is invertible, right, then h of theta is also invertible for all theta which lie in some epsilon ball around a. Why is that so? By the way, why is that so? Because I urge you, by the way, in these sorts of situations, when I ask you a rhetorical question, please pause the video and think for yourselves. But anyway, the answer is, the determinant of h of a is non-zero because of h of a is invertible, and the determinant is a continuous function, so determinant of h of theta is also non-zero as long as theta is sufficiently close to a. Okay, so h of theta is invertible. If h of theta is invertible, none of its eigenvalues are 0 because the determinant of a matrix is simply the product of its eigenvalues, right? So none of the eigenvalues of h of theta are 0. So the only problem could be if h of theta, if all the eigenvalues of h of theta are all positive or all of them are negative, right? That's the only problem. I mean, if one of them is positive and one of them is negative, then you have exactly the same problem as you have here. That is, it's neither positive definite nor negative definite, and therefore you find an h so that f of h plus h is larger than f of a, and you find one more h so that f of a plus h is less than f of a. The only problem is if h of theta is either positive definite or negative definite. Now, if h of theta is indeed positive definite, so what we want to say is that there is an epsilon, so that in an epsilon ball around a, there exists an epsilon ball around a, so that h of theta is neither positive definite nor negative definite on this entire ball. So if this were false, right, so no matter how small an epsilon I choose, if such an epsilon doesn't work, which means if I choose epsilon to be 1 by n, then there is some theta n in that small ball, so that h of theta n is let's say it's positive definite. Okay, it's either positive definite or negative definite, and there are only two possibilities. So for infinitely many values of theta approaching a, h of theta is without loss of generality positive definite. It could be negative definite too, but the same argument would apply. So if h of theta n is positive definite for all theta n which approach a, then what does that mean? V transpose h of theta n times v is strictly positive. Let me write that down here. If we assume that v transpose h of theta n is positive for all v, non-zero for all n, right, then by continuity v transpose h of a v is greater than or equal to 0 for all v, right, which means f of a plus h is greater than or equal to f of a for all h, not for all h. That already implies that a is a local minimum. Local minimum, by the way, doesn't mean that it's a strict local minimum. In other words, f of a plus h is greater than or equal to f of a also counts as a local minimum, right? So that's a contradiction, right? Because we've already said that h of a is neither positive definite nor negative definite, right? So in other words, what this little argument that I've said verbally proves is that if h of a is neither positive definite nor negative definite, then for all there is a neighborhood of A on which h of theta is also neither positive definite nor negative definite, and therefore A is a saddle point. Okay. I have intentionally not written this down because I'd like you to think about this and write it on your own. Yeah. Okay. So so this proves the one direction of the second derivative test in a sense, that is, if your Hessian behaves in a certain way, then you have either a local max, a local min, or you have a saddle point. What about the converse? That is, if A is a local min. Right? Then f of A plus h, so f of A plus h is greater than or equal to f of A for all h and some epsilon, okay, if A is a local minimum, which means is greater than or equal to 0 for all h. Right. Okay, but what we really want v to be greater than or equal to 0 for all v. What we have obtained is only this. Okay, that's not good enough. So how can we prove this? Okay. So the way you prove this is by contradiction. Suppose not. That is, h of A is not positive definite. That is, there exists a vector v not 0 such that v transpose h of v is negative, right? Okay, so how is this going to cause a problem? That means v transpose h of theta v is negative for all theta in some epsilon tilde ball of A by continuity of the Hessian, right? But that's a problem, because if this is the case, that means f of A plus h is f of A plus v is strictly less than f of A, right? For some v, for some v, right? So this is the problem. Right? This v need not, I mean, you might object saying that v, the norm of v need not be small, but it can be made as small as we want by just scaling, right? So the bottom line is A is not a local minimum. That's the problem. Okay. So in other words, v transpose AV cannot be strictly less than 0 for any v not equal to 0. So it must be greater than or equal to 0 for all v, right? So that proves the converse direction. Okay. So now we have proven successfully the second derivative test assuming Taylor's theorem, which Taylor's theorem was proven using the one variable calculus 1, except that we made a claim which we sort of proved, except for a little point which I invite you to think about yourselves. Okay. Right. Okay, so how does one apply Taylor's theorem? That's the more important point, right? So here's an example. So suppose you take f of xy as x square minus xy minus 2y square, and the region of interest is this. Okay. Right. So the question is, find all local extrema in this region. Right. So how does one solve such a problem? The first step is to look at the gradient. If you are at a local extremum, then the gradient must be 0. That's the first derivative test for multivariable calculus, which I verbally stated using the first derivative test for single variable calculus, right? So what's the gradient of this? The gradient is the derivative with respect to x. So when you differentiate with respect to x and hold y a constant, you'll get this. When you differentiate with respect to y, you hold x a constant, you'll get this. So this is 0, 0, if and only if what happens? X equals 0 and y equals 0, right? So if you look at this point, this certainly lies in this region. Okay, so there is a critical point in this region. It may or may not be a local extremum, that we have to check using the second derivative test, but at least we have a critical point in this region. Okay, if I give you a different region, the answer for this such that the origin did not lie in that region, the answer for this question would have been no, there is no local extremum, right? So what's the Hessian? The Hessian is d square f dx square, which is 2, d square f dx dy, which is minus 1, d square f dy dx, which is minus 1, d square f dy square, which is minus 4. Okay. So what are the eigenvalues of this? So you can take lambda minus 2, lambda plus 4, 1, 1, you want this to be 0, which means lambda minus 2, lambda plus 4 minus 1 is 0, which means, I'll write it here, lambda square plus 2 lambda minus 9 is 0. So lambda is minus 2 plus minus b squared plus 36 by 2. All right, so it's minus 1 plus minus square root of 10. Right, so one of the eigenvalues is less than 0, namely this one. This one is of course larger than 0, square root of 10 is certainly larger than 2, right? Which means what? The determinant is non-zero, it's invertible because the determinant is a product of the eigenvalues, so neither of the eigenvalues is 0, so it's non-zero. And one of the eigenvalues is less than 0, one of them is larger than 0, so it's neither positive definite nor negative definite, so which means no local extrema, and 0, 0 is a saddle point. Okay, so the origin is a saddle point, it's not a local extremum, right? So this is how you would solve such a problem. You would simply calculate the eigenvalues. But notice a small little point, at least for 2 by 2 matrices this is very easy to prove. If you take a 2 by 2 real matrix, you don't really have to calculate the eigenvalues. What's the determinant of this matrix? The determinant of this matrix is the product of eigenvalues, right? And so if you take the trace of the matrix, what's the trace? The trace is the sum of the eigenvalues. The determinant is AC minus B square, the trace is A plus C. Now if the product, what we want is for the eigenvalues to have a sign, right? So lambda 1 and lambda 2 are both positive if and only if lambda 1 lambda 2 is positive and lambda 1 plus lambda 2 is positive. Why? Because if these two are positive, obviously these two conditions hold. If these two conditions hold, this would imply that they have the same sign. They are both either positive or negative. But since their sum is positive, they can't both be negative, right? So that means lambda 1, lambda 2 are both positive. So in other words, the determinant and the trace are positive. Okay. In fact, we can say a bit more. The determinant is positive. The trace is positive means that A plus C is positive, right? Determinant is positive means AC minus B square is positive, which means AC is larger than B square. If AC is positive, then A and C have the same sign, either they're both positive or both negative. But because A plus C is positive, that means A is positive and C is positive, right? Which means, and it works the other way around as well. In fact, we can say that the determinant of A is positive and A is itself positive. Because if A is positive, apparently so is C, so A plus C is also positive. So in some sense, the determinant of this 1 by 1 matrix and the determinant of the 2 by 2 matrix must both be positive. So a matrix is positive definite if and only if the determinant of the quote unquote 2 by 2 matrix is positive definite if and only if the first entry is positive and the determinant is positive. In fact, this is true for n by n matrices also. An n by n matrix is positive definite if and only if the first entry is positive, the first 2 by 2 matrix that you get is positive, the first 3 by 3 matrix is positive, and so on. The first 2 by 2 matrix, the determinant is positive. The first 3 by 3 matrix, its determinant is positive. The first 4 by 4 matrix, its determinant is positive, and so on and so forth. Right? This is not an easy condition to prove. It's called Sylvester's criterion. But on paper, this can also be used to deduce positive definiteness because it only involves calculating determinants, because calculating eigenvalues is a rather painful affair, right? You need to compute the roots of a polynomial, which is not always possible. Computing determinants, on the other hand, is rather easy, right? All right, so we'll stop at this point. We'll continue the next time. Thank you for joining.